In this video, we are going to discover tau. This is the Greek letter that's going to represent the pendulum's magic number. So what I want to do is derivate it, and I want to let you know where we got it. So if we set up a table with T, capital tau, that would be the time period in seconds, and the vibration rate is the individual swings back and forth. Now you need to understand the difference. This time period is the entire time in seconds from point A to point B and back to point A. Each vibration, and that would be vibrations per minute at this point, we're simply talking about point A to point B. And then the next vibration is point B back to point A. So let's say I timed a pendulum to half a second. Okay, that's back and forth in half a second. I also counted the fact that it made 240 vibrations. That means it went back and forth 240 times. Okay, I tested another pendulum and it gave me a back and forth rate, a time period of 1 second, and it had 120 vibrations. Finally, I took what we call the seconds pendulum. It takes 2 seconds for the seconds pendulum, the seconds is plural, of course, it takes that pendulum 2 seconds to go back and forth. Its vibration rate is 60 per minute. Taking a look at the graph, we find that as the vibration rate drops, the time period in seconds gets larger. Or conversely, if the time period in seconds gets smaller, the vibration rate goes up. Okay? This sets up what we call an inverse proportion. So let's talk about some definitions real quick. Remember, capital T is the time period in seconds. Vibrations now, I will just call N for number. This is the number of vibrations per minute. Some more definitions here. L is the length in meters. Now I will eventually exchange that L for the small m for meters. It will make things a little easier. And small g is the gravitational acceleration on Earth. It's about 9.80665 meters per second squared. And that's here and there worldwide average-ish. Believe it or not, those decimals are not going to make a hill of beans difference. But it is going to help me with tau. Okay, so definitions again. Tau is the pendulum's magic number, and we're going to go ahead and derive that right now. So let's set up a proportion. I have the time period in seconds, proportional to 1 over the number of beats per minute. Remember, it's inverse proportional. If it were a direct proportion, tau would be directly proportional to n. But it is not, so that's why the fraction is there. Now, in order to set up an equation, we need a constant. So now I have t equaling k, which is going to be our constant, times 1 over the number of vibrations. Rearranging some terms, we find that k equals time times n. Very interesting. And if we replace t with 2 seconds and n now with the vibrations per minute, which we saw in the table, I come out with a constant of 120. Our final equation then is t, time in seconds, time period in seconds, equals 120 over the beat rate in minutes, or n, the number of beats per minute. Now, if we multiply both sides by n, and divided by t, we go ahead and just switch those numbers out. So my beat rate number in minutes is equal to 120 over the time period in seconds. Very interesting relationship. Okay. Now let's replace t with its formula that we found from Galileo, believe it or not, more than 400 years ago. 2 pi times the total of the square root of the length in meters over the gravitational acceleration. What we're going to do next, we're going to factor the 2 out, and that gives us 60 over pi times the square root of length over gravity. And then I want to square the equation. I want to get rid of the radical sign. So that gives us n squared equals 3600 or 3600 over pi squared. And now I have replaced my L with M over G. A little bit of algebra later. We're going to go ahead and rearrange some terms. If you don't know exactly what I did there, you might want to look up Mr. Beeson, Professor Beeson's videos. He has real good algebra videos, and you'll be able to find out what I did there. So nonetheless, I do have my beat rate squared equaling 3600 times gravity over pi squared times meters. Okay, so I'm going to fill in some variables here. I'm going to go ahead and fill in gravity. And since I don't need to deal with m, we're just going to go ahead and multiply that 3600 times the gravitational acceleration. And we come up with 35,303.94. And I'm going to put that all over pi squared, which is 9.8696 forever. Okay, it's just this never-ending number, but I don't know how many digits my calculator went out, but it gave us right here our tau, 3,577.036988. And of course, n squared is that number, tau, over m in meters. So we're going to go ahead and truncate tau now to equal 3577. So whenever you see that little tau, okay, you know that you need to use the number 3577. So let's replace that number now with tau. That gives us our beat rate squared equaling tau over our length in meters. And if we square root both sides, this just gives us our formula for n. So n equals the square root of tau over the length in meters. And if I want meters, I go ahead and simply put tau over our beat rate squared. A simple mnemonic device. Here's a pyramid. I learned it as a circle, but I think a pyramid kind of makes it a little easier to see. You'll notice that our tau is on top, and we have our beat rate squared and our length in meters. Okay? Well, tau is always going to be the top term. So n squared is going to be divided into tau to give you meters, or meters divided into tau to give you n squared. And of course, if you want tau at any time, simply multiply your beat rate squared times the length in meters, and you will always come up with 3577 if you've measured correctly. All right. So we trust that you like this video. Again, tau is the pendulum's magic number, and the mnemonic again is the triangle with t, n squared, and m. And go ahead, like, subscribe, share this video with folks who like mathematical derivations. And essentially, this is a pendulum set that we can apply to music. Again, we'll take care of that in another video. All right, thanks for watching, and we'll see you guys soon. Bye.